Before starting to solve a problem, it's sometimes nice to know its difficulty in advance. If the problem is easy, we should be able to implement an algorithm that solves it relatively quickly. On the other hand, if the problem is computationally hard, there's maybe little hope to solve it for anything but small inputs. There's a whole field in computer science that deals with this kind of problem categorization by using strict mathematical proofs to translate problems to one another. If, for example, it shows that one specific problem with an unknown complexity is just an alternative formulation of another specific problem with a known complexity, then this similarity can tell something about the complexity of the first problem, roughly speaking. Of course, the complexity of the problem translation itself has to be insignificant in order for this trick to work. The very science of problem categorization is rather complex, and we will not even go near that in this clip. Instead, I'll try to explain the nature of a few important complexity categories at an intuitive level, and give some examples of problems that are ridiculously hard to solve. Two of the perhaps most well-known categories are named P and NP respectively. They share an extremely interesting property, as we shall see in a moment, so without further ado, let's dive right in. There's one important term that we need to get in place before proceeding, namely the term polynomial. This is an example of a polynomial. And in big O notation, it is written like this, where we only include the term with the highest exponent and ignore the constants. Here's another example of a polynomial. And similarly as before, it is covered by the functions that are represented by this big O notation. The logarithm is not a polynomial, but an algorithm that runs in logarithmic time is still polynomial because the logarithm of n is covered by, for example, big O of n, and n is a polynomial, a very simple one, but still a polynomial. An expression that is not a polynomial is the exponential function like this one. Notice the difference between the exponential function and polynomials. In exponential functions, the variable that grows, in this case n, is in the exponent, whereas exponents in polynomials are constant. This means that exponential functions grow much faster than polynomials. One complexity category covers problems that can be solved in polynomial time, that is, where the complexity can be expressed as a polynomial. And that category is referred to by the letter P. There is actually no upper limit for the exponent, and in principle, the constants that we ignore in big O notation can be arbitrarily large. But polynomial complexities are still considered as nicely behaving and are, at least by many theoretically oriented computer scientists, considered as the easy problems. So, the complexity category P covers problems that can be solved in polynomial time. We have seen a few of such problems. Sorting was one of them. Another example is list traversals. Computing a hash function and performing a lookup in a hash table is a third and extremely simple example. And then we have various kinds of algorithms for calculating shortest routes in graphs. The complexity class P is large, covering an enormous amount of problems. Another class of problems is named NP. NP is often mistakenly interpreted as non-polynomial, but it actually stands for non-deterministic polynomial time, but that's not important here. Whereas problems in P are required to be solvable in polynomial time, problems in NP are required to be so-called decision problems, and they should be so-called verifiable in polynomial time. But what on earth does that mean? A decision problem is a problem where the solution is either an answer of yes or no. An example could be the problem of answering the question, does a route shorter than some length L exist in a given graph? Here the solution is clearly either yes or no. If the question instead had been, what is the shortest route? then it would no longer have been a decision problem. So it's a requirement that the solution should be either yes or no. By the way, if we should be 100% correct, the complexity class P also formally only covers decision problems, but we can convert other problems to decision problems. So in order to minimize confusion, just think of the problems in P as whatever problems that are solvable in polynomial time. That was a small sidetrack. Back to NP. The second requirement in order for a problem to be in class NP was that it should be verifiable in polynomial time. Verifiable means that in case the solution to the problem is yes, and we somehow, maybe even by magic, are provided with a concrete example that would lead to the answer yes, then we should be able to verify that this provided example would indeed lead to the answer yes. And we should be able to come to that conclusion in polynomial time. If, for example, the decision problem was, does a root shorter than L exist? And the answer to that problem is yes, then the example data should be a concrete root. We can easily verify that this concrete root is indeed shorter than L, namely by simply walking along each edge of the root and measuring the distance traveled. The concrete example data that is used to verify that the answer is indeed yes is referred to as a certificate. Notice that there is no requirement on how this example data or certificate is obtained. It may very well be extremely hard to compute. The only thing that's required is that once we have such a certificate, then the verification should be polynomial. So to recap, a problem is in complexity class NP if it can be answered with yes or no, and in case of a yes, that yes can be verified in polynomial time by the means of a concrete example or certificate. As you can see, I have drawn P inside NP. Intuitively, whenever a problem can be solved in polynomial time, its corresponding decision problem can also be verified in polynomial time, because we can just solve the problem in order to produce the needed certificate ourselves. Therefore, whenever a problem is in P and can be solved in polynomial time, it can also be verified in polynomial time simply by solving it, and therefore it is also in NP. Intuitively, the other way around does not seem to be the case. Just because we have a certificate and can verify it in polynomial time, it doesn't seem like that should imply that we could also solve the problem in polynomial time. I'll leave you with this cliffhanger for now and even skip mentioning specific problems for NP. You'll see why in a moment. The requirements for a problem to sit in NP was relatively loose, so NP covers a large variety of different problems. Some are easy to solve and some are hard. The hardest of the problems in NP are said to be NP complete. Let me give you a couple of examples of NP complete problems. One problem is named subset sum, and it's actually rather simple. Imagine a bunch of integers, positive and negative. The problem is now to answer if there exists any subset of these integers which sum equals 0. Yes or no? Clearly, we can verify a yes solution in polynomial time. If we are provided with a concrete subset, we can summarize its numbers, and if the sum is indeed 0, we have made a verification. To get a feeling about the complexity, you could try to implement an algorithm that solves the problem and experiment with how the execution time grows when the number of integers grows. Another NP-complete problem is the 0-1 knapsack problem with a slight reformulation. Instead of asking to find the largest possible value that fits in the knapsack, we can ask if it's possible to obtain a value larger than some threshold, say v. Now it's a decision problem, and we can easily verify if the values of a concrete subset of items indeed summarizes to v or more. The last example here is the orthogonal packing problem. Consider a rectangular container of a certain size, and consider a bunch of boxes, possibly of varying sizes. The problem is now to decide if the boxes can be arranged in such a way that they all fit within the container without overlapping each other. If an algorithm concludes that a given set of boxes does fit in a given container, we can easily verify that claim against a proposed arrangement simply by placing each box at the coordinate given by the arrangement and check for all boxes that the box is positioned inside the container and no other box overlaps it.